Hey everyone, this is Yash. I've been with Netflix from 2015, working on the Netflix CDN, which is Open Connect, which we'll be mostly talking about today. Before Netflix, I was with Microsoft Azure building data centers for 3 years. So how many people here kind of know the screen, right? Like, great. So this is the Netflix UI, the Netflix product that the end users basically see. As you see here, there are a bunch of stuff happening here. There is videos playing, there is trailers, there is personalization, there is account level information there, and this is all powered by 2 infrastructures. A lot of you might have known from other talks. We have a huge presence on AWS. We've been a big proponent on the cloud from early 2010. And then I'm going to be mostly focused on the other part, which not a lot of you would probably know. Netflix has a content delivery network that is purpose-built to serve all the Netflix traffic. So, as you see in AWS, we have a bunch of microservices, authentication, recommendations, discovery, personalization, playback. You go into any of the movies or TV shows, you click play. There's stuff happening on the cloud to basically, deliver you that content, right? So that's basically what AWS, a lot of the microservices in AWS do. And then the CDN part. So the CDN part is where you actually have all the video being streamed from, like all the box arts that you see here, all the subtitle files, all the JavaScripts that the player needs in real time to basically bring up the UI, all the live player, and stuff like that. We manage DNS for our own services, and then like a bunch of other stuff that we'll talk about more. So Open Connect program in Netflix was started in 2011, 2012. These are basically custom-built hardware on top of FreeBSD. When we started out Open Connect, this was primarily built for video delivery at scale. These Open Connect servers, which we called OCAs, Open Connect appliances, are deployed closer to the end user so that they can have like as much quality of experience as they can. The overall architecture here is a push architecture where we basically take all the content that we encode and we push it out to all these servers. So that when you click play, they're all available in the edge closest to wherever the user is. And the content is basically deployed to all these OCAs worldwide during non-peak hours. So we basically fill these servers, that we call them, from 2 a.m. to like 2 p.m. So that it doesn't, so that the ISPs or the network is really not a bottleneck here. So on the right, as you see, there is a bunch of services. We started with video, as I said, from 2011 to like 2015, 2016. And then we started adding more services on top of the platform. SOD is small objects. So we call video, which are like large objects. And then SOD is like small objects, your JavaScript files, your images, time text, and things like that. FTL is a service that we run. It's called Faster Than Light. It's for accelerating all the API requests from the end user to AWS, so that they don't take the normal internet and we basically use our backbone, which I'll talk later, and we use that backbone to basically accelerate the API performance. We host our own DNS for a bunch of these, for a bunch of our domains. And then recently, some of you might have heard, we launched Live. So Live is a service on top of the Open Connect platform. We talk a lot about like cloud infrastructure here. So I just want to put this picture up. This is basically how our Open Connect servers look inside a data center. This is from Dallas. So we have multiple types of OCAs, like storage and flash OCAs, and they're all like kind of racked in a data center location. We have 2 types of deployments that we do worldwide. This is an IX deployment where we own the rack space, and then we own the servers, we own the routers, and then we connect, we peer, do whatever we want with the servers. And then the second type of deployment is like an ISP deployment, where we give these OCAs to ISPs directly, and then they install these OCA servers within their network, and then so that it's much more efficient for them. So this is the IX sites globally we have. We have about like 70 IX sites globally in almost all major internet exchanges. As you see, we have like a good, we are almost in all the sites in LATAM, bunch in India, Australia, New Zealand, and we are also densely interconnected with almost all the major internet exchange points in US and in Europe. All these IX sites are connected by a multi-terabit backbone, and the backbone also connects directly with AWS. So any of the cache fill that I talked about earlier, any of the control plane traffic that the OCAs have to talk with AWS for, is all traveling through the backbone. This is a little bit crucial for us in terms of managing like delivery. We also have other services like small objects, which fill using this backbone. This is all dedicated redundant capacity. We also have other services like the FTL API traffic, which basically gets terminated in any of the closest IX locations, and then they all get routed to the nearest AWS region. This is our overall map. This includes all our IX and ISP sites that we have globally deployed. Right now, we are about like 230 million members. We have about 18,000 plus OCAs that are currently deployed worldwide. This is in 6,000 locations and in 175 countries. As you see here, almost on most of the major ISPs, we are deeply embedded. We have a direct relationship with the ISPs. So we do this so that they don't have to carry any of the traffic over the internet. It's all like locally offloaded. And it's a really, really efficient for both Netflix and also for the ISPs. So this is a high-level diagram of how stuff works once you click play. So as soon as you go find a movie or a TV series that you like, you click play. Like we are almost in almost all of the client devices. A playback request is basically sent to AWS, which is our any of our API services running there, and then the playback apps basically determine where you're coming from, what content are you looking at, are you able to like play that content, what kind of resolution that needs to be provided there. And then it basically pulls out all the downloadable IDs that we call them for a particular movie. And then they basically ask our other service, which is the steering service called Coda, which basically has all the information about all the OCAs, their health, are they, we basically route based on BGP here. So the content service there understands whether OCAs are healthy and is it good to stream this content to this particular OCA. So they basically generate all the URLs that are necessary and then send them back to the playback services, and then those get sent back to the client devices. And then the clients directly stream any of the content directly from the OCAs that are closer to them. Let's say if you are in San Jose in Comcast, you're going to be like you're not going to be like streaming that content from like New York or Washington. You're going to be like streaming that content mostly from a data center that's like close by. Similar, let's say if you're in India, in Mumbai, and if you click play, you're going to be like talking to the closest AWS region, and then that region basically determines which OCA is closer to you, and then you're going to be streaming this content directly from Mumbai, basically. So it's, you have, from an end user perspective, you will have like a much better QoE, and it's just like more efficient in general. Since this talk is about resiliency, from our understanding of running these, running the whole network for the last like few years, we think for the CDN domain, there is two types of failure domains that we have seen. The first one is the infrastructure failure, and the second one is like, I generally categorize this as like software failures. So infrastructure failures, think like fiber cuts, power outages, line card failures on a router, and then you have like sometimes there's a storm coming in, and all of a sudden you lose like the primary and the redundant power in the data center, and then the data center goes offline. Usually we see, whenever we see these kinds of failure, for us, it's usually very localized to a particular market or a particular set of ISPs or an ASN. And most of the time, it kind of recovers by itself. The other kind of failure that we see is software-related failures, where we push out a firmware that passes the canary, but then something only surfaces after you hit like a certain volume of traffic. So that is that, and then we also have config changes, where even if you slow roll some config changes, a bug or like a secondary impact would only get surfaced much later in the process. So that affects like a large number of users, and that's usually like a major incident, because there is not a lot of fallback in that scenario. So if you again go back to the map, like for example, if you have like a major fiber cut in Washington, that's going to affect like maybe like 6 ISPs and affects like maybe like 1/10 of like your traffic at that point. So this is basically what we call it as like an infrastructure level failure. Since we have about like 5,000 locations, and there are only 70 sites that we control, and all the remaining sites are all ISPs, and we don't really control them, and that's all within the ISP's network, we see these kinds of failures happening like day in, day out from a localized perspective. We have like sites going online, offline. You have OCAs getting from unhealthy to unhealthy for like n number of reasons. So most of our effort in general for resiliency has been focused towards this kind of infrastructure failure, where we need to retool our Netflix clients and our design and architecture that we come up with to make sure that we don't really get like the Netflix clients have like enough resiliency to handle these day-to-day outages that keep happening, like the internet weather kind of outages. This is the type of outages that we really don't like. This is where you have, it's very hard to have like 6 different fiber cuts around the same time in different continents, right? If it happens, we can't really do anything, but usually this doesn't happen. This is mostly caused by us, where we basically shoot ourselves in the foot. And the resiliency practices that we follow in the cloud kind of apply here, even though these are all physical servers, because it's the same kind of firmware rollout. The principles are the same, but the implementation is different. Because you're like in this case, you have like a finite number of OCAs, and let's say if you're running a firmware upgrade, it's going to take like one and a half hours to reboot a server, and then for the server to come back up and stuff like that. So we really usually are very slow and careful when we are doing these fleet-wide like horizontal changes, which like a change that affects each and every server. That is something that we are always kind of aware of. So in this, for the remainder of the talk, I'm going to be mostly focused on the infrastructure level failures, and I'm going to take you through a bunch of scenarios and explain like what we have done to kind of like improve the resiliency for the Netflix clients. So there are 3 types of failure exercises we do, or these are like the 3 I thought would be like really, really useful here. First one is like a stack failure. In the IX sites that I've shown before, each site is going to have 2 stacks, like completely redundant stacks with like same capacity. You call it like A and B. And most of the traffic that's coming to the site would be like load balanced between those 2 stacks of servers. So that's stack failure. And then I'm going to talk about stack overload. And then I'm also going to be talking about other resiliency exercises that we do for other services. Like one such example is like Anycast. So this is a typical IX site for us, where you have a stack of servers that has all the content, and then the other stack of servers which has exactly the same content. And then you have 2 routers, and they are all connected to the internet through using peering points or through the general internet. So what we basically do is we basically take a stack, and during peak, we basically shut down a line card. And then we basically induce like a failure, like a real failure on customer traffic. We usually do it at a peak. If you pick a site, and if the peak is like Eastern time or Pacific time, we basically pick a peak time, and we basically fail this. And this is not really like a synthetic traffic. This is like hundreds of gigs of like actual customer traffic that we actually fail. So we basically shut down shut down like a line card, and then all of a sudden you have stack A that basically goes offline. Another important thing to talk about here is the Netflix clients. In this case, we own the logic in the Netflix clients, and then we also own the server infrastructure. So we have developed both the server infrastructure and the Netflix clients in such a way that they basically talk with each other in like a very synchronized fashion. So what I mean by that is basically the Netflix clients understand the internet weather. The Netflix clients understand that these servers can go off at any time, right? So if you pick, like, if you go to Netflix app and if you click play right now, you're not just going to get like one particular stack. You're going to have 3 distinct failure domain stacks. So you'll have stack A, stack B, and then stack C. So the idea here is like if a stack A goes down, then the Netflix clients would figure that out on their own without talking to the control plane, and actually seamlessly switch away to the stack B, so that the end user doesn't even like recognize that, oh, like we just lost like a huge stack. So we have something called adaptive streaming engine on the clients, which basically you have like to kind of like do the one-on-one on this. It's basically you have a buffer, and then you're trying to fill that buffer up, and then you're on the other side you're basically like taking all the frames in that buffer and you're like sending it to the player. So you have this thing going on, and there are multiple things here. So as soon as you click play, we want to make sure that the play delay, the initial rotation that happens is kind of like as low as possible. And then we want to make sure that we take you to the highest quality video as soon as possible. And then we want to also make sure that we have as low, or like we don't want to have a rebuffer at any cost. So there are some certain principles that the client devices have the adaptive streaming engine like developed on, which we usually work very closely with the client devices to make sure that they understand the risks and the implementation here. So this is, right, like, so on the right side is a graph where you have a site with about 500 gigs of traffic. There is stack A and there is stack B. And then you pick a time just before peak, you fail a stack, and then you see automatically the clients like switching away to the secondary stack, and then you basically like make sure that there is we don't drop like 200 or 300 gigs of traffic on the floor. So usually there's a time of failure, and then there is T plus 5 minutes until the control plane recognizes that, oh crap, like this stack is like actually offline because the OCS stops sending health. And then it basically readjusts all the routing or the internet map it has for those sets of clients. So there is like 2 different scenarios here. You need to make sure the thundering herd of traffic that goes to the second stack from the failed stack is handled well by the OCA that receives it, because all of a sudden you have like an OCA with like maybe 10 gigs of traffic, and then all of a sudden you have like 30 gigs of traffic. So usually, for the server infrastructure, you have like a sinusoidal way of like traffic, but in this case, it's like a very sharp increase in the number of connections and so on. So we need to make sure that we look at the OCA, we tune the OCA, and we make sure that the OCA actually handles this thundering herd of traffic. We look at errors, the client errors. Like, do we have an increase in client reported errors for that particular market or that particular ASN that we are running this test on? We need to make sure that that is as flat as possible. And if there are errors, then we need to go on and look at why this client is not efficiently switching away. And then control plane. We need to make sure the control plane actually reacts as quickly as possible. OCAs in this time usually reports health every 30 seconds. So we need to make sure that there's a 30-second for the OCAs to report health that is being missed. And then there is a propagation delay for control plane to figure that out. And then there is a time when the new URLs, when it's generating the new URLs, it doesn't really take this stack into account, and it basically marks this stack as like this is out of service. And then we monitor Twibber. So and then we monitor QoE. QoE is like a huge part in how we operate within Netflix. That's like one of the primary indicators for a lot of the tests we do. So Twibber is basically your average bitrate. If you are running, if you are a 4K TV wanting a 4K bitrate, we want to make sure that we do everything possible to give you that 4K quality, right? Like, so that's Twibber basically, which is the average bitrate. Play delay, again, when you click play, can you show the first frame as soon as possible, right? If you're waiting for like 10, 12 seconds for a play delay for a movie to start, that's probably like not a good experience. Rebuffers, the one that we all kind of dread, where you're in the middle of the show, all of a sudden you see the spinning wheel. We don't want to give that, and we want rebuffers to be like as slow as possible. So these are kind of like the high-level things that we look when we run these tests. So there's, again, I'm just recapping. So you have a time of failure, and then you have time t plus 6 minutes. That is the adjustment phase for all the systems involved. And then the t plus 6 minutes is like however long the stack is offline. We want to make sure that the systems are reacting as seamlessly as possible. Since we are deeply deployed, like I said before, we have these kinds of scenarios in like almost on an everyday basis. Mostly not in IX, but on ISPs. We have deployments where we have a single OCA in a site to like tens of OCAs in a site, right? So we have like these kinds of failures kind of happening all the time. The main objective here is like we don't want to be paged for this. We want the system to basically behave in a way that we design it to behave. We want the system to kind of auto heal by itself. It would be like really bad if we get like paged or if we have to go on manually to do stuff when like a bunch of servers are offline. If the clients can automatically like switch away, switch down bitrate if needed, and kind of like seamlessly come back when the stack comes online, that's probably the objective here for us. So this is the stack overload test. So this is another scenario where you have like a bunch of capacity. This is not the cloud where you can just like spin up a bunch of EC2 instances and then kind of scale up as the traffic comes in. This is all physical servers that have to be like made and then shipped and then past customs and then actually go into like some location, and then you have like people working on the racks to basically install them, bring it online. So capacity, the way that we do capacity is not like that shorter of a time frame. It's usually like lead time of like you're looking at like 6 to 8 months to add capacity in some regions. So we need to make sure that there are situations where we have these unintended consequence, where a show suddenly becomes like too popular. And then that's a good problem to have, but usually we have a 30 to 40% headroom. But then that, for like a very short amount of time, we've seen time and time again before that a show becomes like too popular, and then all of a sudden you have like 3x the number of traffic. Now you can't really add capacity, and it's not wise to basically turn away those customers who are just like signing up for the new show. So we do something called stack overload test, where we take like the same A and B stack, we basically like soft turn off stack A, and then we basically double the traffic to stack B for like an extended period of time. The stack failure test that we do before is usually during peak, and then we basically bring the stack back on, and then that's done. But this is usually done for like weeks, at least a week to at least like 2 weeks, where we make sure that we overload like a set of servers to, if they are like in this case, if you're looking at this is stack A and B doing they're kind of like align on the line, so you probably don't see the blue line before and after. But you see a stack doing about 420 gigs at peak, and then we turn off a stack, and then all of a sudden you see the other stack doing about like 800 gigs at peak. So in this case, we'll be looking at whether the OCAs are basically behaving properly when they are like completely hammered, and we want them to melt, and they are like at 100% like all the time for like a week. What does that do to the clients? Are the clients behaving properly when there are some like, so obviously the latency would be like a little bit higher for the clients when we do this overload test. So we want to make sure that the clients are able to handle this like perfectly. We look at similar metrics like Twibber, play delay. What happens to the play delay when when a client started their stream to this overloaded stack? Right? This was actually like, we started doing this in like 2018, 2019, and then COVID hit, and all of a sudden we had this like huge increase in traffic, like how others would have probably seen this as well. And this is like doing stuff like this actually like gave us like a lot of confidence that yeah, we are going to be okay. We know exactly what our OCAs would do. We know exactly what our clients would do. We just did this like 3 months back. It's just that it's just stuff like this is happening at like a much larger scale. But we kind of like know what we did. It kind of like paid off in situations like this. Yeah, so again, just at the high level, at least for us, this helps with the frequent ISP and IX failures that we have. For most of these cases, we'll just like kind of let it go. We'll let it auto recover on its own. There is sometimes where if there is like a major fiber cut in an area, we might lose like a site completely, where you have both the stacks like kind of going down. So that the stack failure test that we do kind of like covers that scenario pretty well, along with the overload test we do. Yeah, like I talked about, we have this helps with like situations where we have content getting popular, or all of a sudden you have like a whole country having like 20 to 30% more traffic because of a popular show. In most of these cases, like except for when we have a network failure equipment on our own, we don't really like do much. We just like let it recover. We just let the systems kind of handle these failures gracefully and kind of recover on their own. The important thing is we have like a very close loop between the OCA, the client, and the control plane. So all the three systems have to be in sync for these failures to basically like handle gracefully, and then this needs to be like tested again and again and again, make sure that any new changes that we bring in doesn't break this resiliency functionality. That's really like top of the mind for us. Even though a lot of these things are happening on the while, we do go and like do this like occasionally, where we take like a huge site and then we fail them during peak. Because we roll firmware like every month, and then stuff in the cloud is getting changed. We have the clients that are getting changed. We've seen regressions before where we might expect a behavior from the client, but it might not happen. But it was happening like 6 months back, but it stopped happening now. So we need to like work closely with the client teams to make sure the resiliency that would expect for the CDN is kind of like they're up and running. Yeah, so the two exercises that I talked about was primarily for video. Like I said, we also have like a bunch of other services that we run. So this is an example where we do these Anycast failure exercises. How many of you here know what Anycast is? OK, right. So for people who don't know, it's basically like you might have gone in and configured 1.1.1, 8.8.8.8 for your DNS, right? So that's basically like Cloudflare's and then Google's like IP address, which is basically Anycast, which is Unicast is basically if you have a server IP, you connect to it. There's a single server. In this case, if you look here, we have these I've just selected like a few sites here, but you see the routers here advertising the same IP address across like multiple different domains. So basically, that's Anycast. So we have we have our small objects and FTL using Anycast domain. So Anycast is like kind of a critical service for us now. Basically like. We were kind of like talking about this internally. Okay, like we do this like for we call video SWOT. We do this like really well for SWOT, but what about other services? Like what are all the failure domains that we have there that we can actually like test and then kind of like get better at basically. So one such example is Anycast. So the primary thing that we thought about Anycast was, if we don't shoot ourselves in the foot, then basically if we are looking at an infrastructure level failure or like a internet routing failure that might happen, which has happened in the past, which basically has took like a portion of Anycast out of rotation for like a particular region, right? So what we started doing was we started pulling Anycast from like a bunch of different sites in our IX sites. And then we looked at where the traffic went. Like how does with video, it's all tiered traffic, where we know like a particular prefix is going to go to a particular site. But for Anycast, it's not the case. So we basically started pulling Anycast out of different sites initially, and then we started finding out, okay, as soon as you pull Anycast out of a site, what really happens? Where is this traffic going? And you would expect a traffic, let's say if you pull out Anycast from Seattle, you would expect the traffic to go to like San Jose. But sometimes you would expect traffic, you would end up seeing the traffic in like Washington or New York. So you know that the Unicast routing is different. You know that the Anycast routing is different. There are some things that we have to go and fix, work with our partner ISPs to make sure that, hey, you need to like adjust the routing to make sure that the Anycast is actually on a preferred destination and not going to someplace else. And then, so initially we started doing this, and then we were like, okay, what happens if there's like a regional failure for Anycast? And then that's exactly what we did. We picked all the sites for different regions in each of the continents, like LATAM, Europe, like Asia, ANZ, Australia, New Zealand, and then we just shut off Anycast for all the particular region, and then we started seeing where would that traffic show up. Like if Anycast goes down, would we have like an actual like a proper outage, or is it just like a latency miss, or is it just like an increase in latency, or would we actually have like an issue? We did find like when you start shutting down like stuff in like Africa, like Johannesburg or in Nairobi, you do start seeing that the clients get timed out after 3 seconds because their nearest destination is like Frankfurt or London, and then it takes like 2.5 seconds for them to get there, and we did see like a lot of issues there. So we kind of knew that okay, this is probably like the extent to which we can test or what to not test here. In most of the cases, we are looking at like we also measure our app TTR, where the amount of time it takes to like resolve like domains when you launch the Netflix app, or even on Cadmium, even on like your Chrome browser. So we measure latency. We want to make sure that if you see like 6 gigs of like Anycast traffic in a particular region, are we seeing the same 6 gigs somewhere else? Are we losing traffic? Are we having like an increased errors for some device types and stuff like that? Yeah. I just want to quickly talk about the latest one that we did. So I don't know if you have noticed, if you all know, but we launched our first live event back on March 4th. It was a Chris Rock special. So live is basically a service on top of the OCAs. Right, so like I showed initially, so on the OCAs as a platform, you have your video service, you have your small object service, which does all the images and box art and stuff like that. And then live was like an additional service on top of the OCAs. So when we didn't, at least for this one, we didn't have a lot of time like before. We had to like develop and onboard this service in a matter of like 6 to 9 months. So basically, we started developing it, and then we were like, okay, it's very similar to SWOT, which means that we need to have exact same resiliency capabilities as SWOT to live. So what we did was even when we were in the middle of development, we started bringing up all the resiliency stuff that we have for SWOT, and then we started testing those. So basically, when even in like Jan, Feb, we started doing stack failure exercises. We started doing origin failure exercises, and then we kind of like made that flywheel keep rotating. Even though it was a new service, we didn't treat that as like a hey, this is like just like a new service. We'll come to resiliency like later once this is all settled. Once this all settles down and this kind of becomes like a prominent service, we kind of didn't do that. We kind of like were like we'll make sure that whatever resiliency we have for SWOT is there for live, because our members really don't like distinguish between like SWOT and live. And if you go and watch a live content, you are like, oh, maybe like Netflix developed it new, so they don't have all these capabilities. We don't want to kind of have that kind of mentality going in. So when we went live on March 4th, our clients had the switch away capabilities, and they had almost the very similar capabilities for like switching down bit rates if there's a congestion, to error out more gracefully, to kind of like auto recover if there are failures. So we kind of made sure that from day one, this is not really like an afterthought, but like this is like right in the front and center of kind of what we do for operations when we went live. In this case, since this is not a push architecture, this is a pull architecture, where you have a live event happening, and then you have like 25, 30 seconds where that whole frames have to be like all transported to the encoding, and then it has to go through the Netflix services. So the architecture here is like a little bit different. So the failure domains were a little bit different. Even though we didn't go and like do a lot of work to like cover all those failure domains, we made sure that all the major failure domains were kind of taken care of and were actually like addressed. So we felt like pretty good during the launch that whatever the stuff that happens for SWOT, if the same failure happens for live, we know exactly like what would happen and stuff like that. Just a quick takeaway. So we always like have this thing where we don't really like want to shy away from a failure. I used to joke internally that I kind of like outages, because like they kind of help you to like learn a lot. They kind of help you to like go deeper into systems where you might not be like going deep. So that's kind of our operating philosophy. Like we need to make sure that we plan for failure, we embrace failure, and like resiliency is like a big vertical within the within OpenConnect. Where it's not just like ops people or like reliability team is thinking about it. We make sure that this is within all the sister teams, like Open Connect development or like the control plane teams, to make sure that, hey, we need, like, whenever you're thinking about a feature, make sure that you think about like all these failure cases and make sure that when you release the feature, this failure case is all like taken care of, so that we kind of keep the the excellence on the resiliency that we have up. We try to look for patterns, right? Like, so this is like a cat and a mouse game to the most extent. We're never going to say that, oh, this is all done kind of deal. But there are patterns that happen like all the time. And there are some patterns where it might take you to a wrong end, but there are a lot of patterns where if you persist long enough, you'll start seeing like bigger patterns emerging out of it. And then that kind of helps you to go deep into like certain areas and then actually like devise these exercises and then go back to the development and then say, hey, we have this problem where this cascading failure is okay, but this cascading failure is like not okay. I think we can do something about it. And then make sure that you work with like all the teams to make sure they understand it, and then you kind of like take care of that situation. Yeah, culture is like another big thing. If you're trying to like do similar things, what I've seen is like if everyone has like the same culture and like wanting to not fail, and if it fails, fail gracefully, and you have all these principles in mind that a lot of you guys are already aware of, then that kind of helps with like communication. Yeah, and the other thing is like we always try to make sure that we talk about it like all the time. We do these exercises, we make sure we publish all the memos out, we ask questions, we make sure that we go as deep as possible, and that kind of excites us. Once we put in a lot of work to do all these things, then everyone is usually on board to say that, okay, yeah, we also don't want all these failures to happen, and let's do something about it. That's all I had. I can take questions. Thank you so much.